My name is Ankur Sheth. I'm going to walk you through a demo of the AI data center test platform. So let's jump right to it. What is our demo setup? We're emulating and we're looking at a server that has 8 GPUs here, okay, with the NICs, and it is connected to a 2-tier fabric, a flow network. This is classic net data center topology that is used, and seeing the effects of the workload on this network. So instead of the GPUs and servers, we're going to use our Aries-1 box that emulates the GPUs and the NICs. We're emulating 8 ranks of GPUs that are doing communication over these 400 gig links on the network. Everything is 400 gig. We are the server at the bottom, Aries-1. The fabric is the real fabric. We're sending real traffic through that fabric and seeing how it behaves. The 2 scenarios we're going to look at is first congestion in the fabric. Okay, we're going to do an A versus B comparison and seeing how the fabric behaves under different configurations. And then we're going to look at how a network designer can improve throughput by using QP parallelism. Okay.
So is this using workload replay or?
This is Keysight Collective Communications Benchmark. We're looking at collectives. Okay, so this is our home page of the application AI Data Center Test Platform. We've got our applications here, and we've got some old trial reports that we have saved. We're just going to use that, and I'm going to use that to demonstrate the product. We have a bunch of trials that we ran earlier and the results which we have saved for us to look at right now, and that's what we're going to do. Each test can take a few minutes to run, so in the interest of time, we're just going to walk through the results, and I will walk through what the configuration is and so on and so forth. So I'm going to save the old trial. And so this is the configuration page. This is the first page in the benchmark, Keysight Collective Communications Benchmark. 3 parts to it. There is the benchmark configuration, and I'll talk about that. There is the infrastructure that we want to emulate, and then there is the information about our chassis that we need to be providing. So we are going to run what is known as the all-reduce collective. All-reduce collective is typically used during the backward pass of a training job, okay? And the premise is that all the GPUs have some amount of data that's unique to them. At the end of this operation, you want all the GPUs to have a result that was obtained by combining all that data, okay? So you have 3 GPUs with A, B, and C as the data. You want something like A plus B plus C, that result, to be with all GPUs at the end of that collective. And there's multiple different algorithms that can be used to achieve this. There is something called a unidirectional ring, and we'll dig deeper into that in a minute, that we're using for the first one. We're saying all the GPUs have 4 gigabytes of data, okay, that they have, that has to be used for this computation. And we're using RoCE as the transport, that is RDMA over converged Ethernet. We're going to use 4 Q-pairs. So Q-pairs is a term that comes from the RoCE transport protocol. It's just a different way of expressing a connection, just without going into more details. There's many more advanced parameters that can be configured. We don't need to look at that. We're going to emulate 8 hosts, each with 1 GPU, okay? And that gives us our 8 GPU count. We're going to then map that to the Keysight hardware. And so if I go into configure, these are my 8 ranks that I'm emulating. And this is the Keysight chassis, the Aries 1 chassis and the physical front panel port that I'm going to use. So chassis at this IP address and port number 1 is going to be rank 0 in my collective. Okay? This is what that port is representing. We have full information that you need to provide for the network aspect, IP addresses, gateways, and so on, and many more Ethernet properties and congestion properties and so on. Once I've configured everything, I can just run the trial. We're going to skip that right now, and we're going to go directly to the statistics that we obtain. Okay? So
does each host in the simulation have
one GPU.
One
right
GPU.
now, one GPU. We're emulating one GPU. We can emulate 4 GPUs, even 8 GPUs. For the purposes of this test, it is 8 hosts, each with 1 GPU.
And that's to maximize dependency on the network rather than the
Exactly. We don't want to worry about the internal communication that happens inside a host right now for this particular test. So we'll look at the statistics, right? And the first thing we want to see is this summary. The first thing we're going to see is summary. So this is static data, the first 2 columns. This is the amount of data each of those 8 GPUs had. This is the collective we are going to run, all reduced. And so what we are saying is that it took, when we ran this traffic and this test in this unidirectional ring format, it took 616 milliseconds, okay, to run and complete this computation and this exchange. That gave us a bandwidth for the algorithm, which is about 7 gigabytes per second. Now recollect that we're running on a network that is 400 gigabytes, 400 gigabit Ethernet, right? This is pretty low. This is pretty low. This is not something I like to see. And if you look at it, the ideal compared to the throughput that we could have obtained, theoretical throughput we could have obtained, it is only 25%. Okay? That's pretty low. We don't want to see utilization that is this low. So I need to drill down deeper why I got such poor performance. And so we have these detailed flow completion times. And you can see that my 95th percentile and the 100th percentile latencies, flow completion times in milliseconds are way off compared to the 50th percentile. My 50th percentile is 36 milliseconds and my 95th percentile is 67 milliseconds. Pretty far off, almost double, not good, right? Let me drill down deeper into that. And so we get this nice graph that shows how the data moved through the network. Okay? What are we showing here? We're showing the 8 ranks on the y-axis, and we're showing time on the x-axis. So each line here represents one chunk of data transfer from one rank to another.
When you say rank, you're talking host?
GPU. Rank is a GPU for now, our purposes. Okay. So what this is saying is at time 0, GPU 0 started transmitting and to rank GPU 1, right? And that took 38.81 milliseconds, 36.81. At the same time, rank 1 started transmitting and it took 36.85 milliseconds. Once it received that data, it sent it over to the next rank and so on, right? And we can see how that entire data moved across all the 8 GPUs in a ring-like manner. 2 steps. In the all reduced, the first step is I send to the next guy, he did some computation. With the intermediate results, he sent it to the next guy after that, and so on. At the end of that one ring,
seems like between 3 and 4 is an abnormal delay.
Yes.
And it happens both times.
It happens both times, right? And we see that the slopes of each of these lines are not the same. This is the throughput. So some data transfers are taking longer. It's the same amount of data that is going from each rank to rank, but sometimes it's taking longer. And this is where the latencies accumulate. And you can see that the transfer here is the one that completed the last. This particular ring completed the last. Full data is available further down. Okay?
So in every case here, between 3 and 4,
Right.
it looks like there's a problem between
there's a
those.
problem somewhere, right? And I look at the cumulative distribution function of those latencies. Cumulative distribution function is essentially telling me what percentile took how much, what percentile of flows took so many milliseconds or less to get transferred, right? And I want to see a straight line in a good network. This is not a straight line, right? This is telling me that roughly 50% of my flows took 37 milliseconds, but look at this long tail here, right?
So is it fair to say that in every one of these communications, the data, the transfer size is identical?
Transfer size is identical.
Completely identical.
In this particular algorithm, it's completely algorithm.
It's right. So
Yes.
in this case, it's completely identical. So in a perfect world, every transfer should take the exact amount of
Exact same time, but it does not. In this case, it's really bad.
Of, because zombies in the network.
Because my
static.
network is not well configured for this particular scenario, right? So when I look at this, I can go back and I check, and we see that the network was not properly configured for congestion control. Okay?
Okay.
Now let's see what happens when I change my network configuration. No change to what I'm sending. What kind of results we get? Same configuration, everything is exactly the same, but let's just look at the completion time. 163 milliseconds. My utilization went up to 95. Now this is perhaps a little too good to be true, right? It's still a little synthetic, but a change in the network, same amount of data, same patterns that we are sending, same number of packets, everything is exactly the same. We fixed our network.
So what did you change in the network?
The network was not correctly configured for congestion control, and the particular thing that was not correctly configured is the PFC settings. So PFC is priority flow control. It's an Ethernet layer congestion control mechanism, and it is hard to configure it correctly. It is very easy to misconfigure it or end up with poor configurations.
And does your tool provide instructions on how to do it properly? No. Okay.
That is often an art and a science. Configuring networks properly, as Alex will tell you, is as much of an art as it is science.
So most vendors tell us that AI would do all this for us.
Not there yet. This
So
is
I know,
helping them. This is us helping them get there.
I just predict that in 6 months, that's what you'll be telling us too.
Let me chime in here. We do have customers who are using our platform to improve their orchestration capabilities of the management layer. And they have internal demonstrations where they can automatically configure the congestion control parameters to improve throughput. They use us to send traffic to measure how well they perform, and they feed that into their centralized controllers, and thus make it, not require human intervention, right? They try to optimize it.
Yeah. So in this data visualization and the grid and everything, like you pointed out that that there were differences in the flow where you could see it took longer. Which call was that completion time?
Completion time.
Okay.
That's what we're really looking at.
Okay. So I would expect I can do data, but we all know data viz is what makes it all sexy and everything. Like I would expect your visualization to highlight those anomalies or the, I don't
So we
use
have
the
full
word rank,
filters
but
here,
yeah.
right? We have capabilities of all kinds of filtering here.
Okay.
You can do filters based on completion time greater than this and so on and so forth to easily highlight. Oftentimes, it's not just one particular thing that we want to highlight.
Yeah.
Depending on who our customers are, they want to look at different aspects. And so we've not yet gone very deep into this.
Okay.
Yeah,
Thank you.
that was partly where I wanted
So,
Yeah.
to ask questions.
if you look at this, right, in the interest of time, I just want to keep moving. If you look at this, all lines are parallel. The slopes are very well aligned.
You cheated.
Guilty as charged, right?
Mean.
These come across pretty,
Yeah, it's a
they
pretty strong
complete
curve
pretty
for another one, yeah.
close, right? And if you look at it, this is as good as we can expect. Now, here is what we can do really well. You can zoom in. There is even tail latencies, but it's really small fractions of milliseconds that are coming up here. But look at the data that we can go to and the level of detail we can go to, right? This is milliseconds or even microsecond differences that can be shown very easily here.
But isn't that completion time column? I didn't memorize it. I just noticed that the 6 was the highest number in the previous trial.
Let's sort it.
Oh, okay. That's what the difference is. Got it.
6.9
Got it.
versus
Yeah.
11.
Got it. Okay. Thank you.
So when they're using your tool, would the network not be doing normal training or inferencing? So when they're doing
This is
this
an
sort of
isolated network.
this
right?
is an isolated network.
This is
so
an
this is a
isolated
test network.
This is a test network.
I see.
The device under test.
The device under test or the system under
Demo
test.
network. I'm sorry. Demo network.
More or less.
Yeah.
So are you seeing that CI integration as being an element of this? How to
Yes.
tune?
So what is it that people, when we talk of CI, what is it that do, right? All hyperscalers are building their own networking products right now. They're rapidly iterating. New versions of software, new versions of hardware are being pushed out daily. Before they push it out to production, they need to run a series of testing through their CI. They're incorporating us into those CI pipelines.
And this is the place where you can get some science into the design of that PFC. Is for this particular workload, this is the configuration that I do, but I'm not doing it by, there's a formula from
I change my ECMP hashing, right? Typically, let's just say I have one version of software that I have deployed in my fleet in my data center right now. And Alex came here and said, hey, I changed our ECMP hashing and it is 10 times better. I want to make sure it has not broken anything else before I even look at whether it is better or not. And that is what the CI pipeline is going to do.
So in a time and motion study, not using that versus using that, what are your customers expecting to see?
What are they expecting to see? They're expecting to see that their device, first of all, is operating within that narrow band of acceptable performance that was achieved earlier, and there's no degradation.
Okay.
That is the first and foremost.
Okay.
Right? They're expecting to see that the capability that he built, it came with some test cases and things like that, is really saying what is really acting according to what he said it is going to do.
So from a project timeline, if I wasn't using any of this, how long do you believe that would take versus I am now using everything you've just shown us?
Alex, you have any data on that? I mean, automation is a reality, right?
Yeah,
and this has been around for a long time in industry. It's really a question of...
Okay. Yeah, so to actually get the data, you got to go through at least a single NPI cycle.
Yeah.
Those cycles typically take 18 months. This is we're just releasing this product. So give us time.
Understood.
We will have data later.
Very good. Very good.
Okay, let's move forward. So this is one experiment, right? I want to show you another experiment now where we're running a different algorithm. It's still running an all reduce, but we're running what is known as a halving doubling algorithm. And the unique aspect about this is the data at each step is a different amount, okay? And we're running it with one queue pair. So every two GPUs are communicating over one queue pair. Think of it as one connection, okay? We're still emulating 8 GPUs, right, in 8 servers, and we're going to see what it looks like when we run it. And we see a completion time of 285 milliseconds and performance which is about average, 53, nothing great, right? Nothing to talk about more. You look at this, and this is the graph that shows you the data movements. So the first step, you're transmitting half of the data. Out of 4 gig, you're doing 2 gigs. The next step, you're doing 1 gig, and the last step is one half gig, right? 512. So 4 gigs is the total data. In my first step, I'm transmitting 2. In my next step, I'm transmitting 1. In my third step, I'm transmitting half. Okay? And straight away, my lines are not parallel, which is what I want to see. Not really great, right? I can look at my CDF and I can see long tail latencies, right? So it doesn't make sense to compare the time it took to transmit 1 gig of data with half a gig of data. You would expect it to take less time. So we have 3 different sizes of data being transferred through the network as part of this algorithm. And we want to see the time it took to complete on a per data size basis. And that's why we end up with 3 lines on the CDF. So this line is what the completion times for transmitting half a gig of data. This line here is the completion times for transmitting 1 gig of data. And this is the completion times for transmitting 2 gigs of data. And you can see that when the data sizes got larger, our tail latencies really became bad. At half a gig, it is still okay. But look at this. At 25th percentile, we are at 44. And at 50, we are already at 66. Huge discrepancies. Something's not looking really that good. Now, I'm going to change my configuration. And I'm going to look at same test, but with more queue pairs. Okay, so same all reduce 4 gigs of data, halving doubling algorithm, but instead of 1 queue pair, I'm using 8 queue pairs. This is a change, say somebody made at the NIC level, right, in the library, the software stack. So I am the network designer. I noticed this is what is happening, and I go and tell the software person who's running his stack on the host, make this change on your side. This is not the network change. This is now a change on the endpoint, right? And
so how would somebody have potentially diagnosed that? I mean,
you would see that you're not utilizing the bandwidth very well. But you would see that I have a lot of hash collisions in the network because there is no entropy. All the data is transmitting over one connection. So it's.
Do you have some sort of logging that would show that? I mean,
this is just things that you would see from the telemetry of your fabric.
You're running on the AI systems. You're running metrics to keep to understand how busy your GPUs are. So you would see at very gross level, you would actually see GPUs.
Yes, yes,
that
you
have high idle times because they're waiting on data.
You would potentially see these things, but other than just seeing that they had contention or they were having delays, how would you actually go about diagnosing what the problem is?
So you start by looking at what we are reporting. That's first of all,
okay.
And then you have to start correlating to the metrics and the telemetry you're collecting from the fabric. So in this case, you will see that there are some paths in your fabric which are hotter than some others. Load is not getting distributed evenly.
Okay.
Okay. And so running it again, we see with 8 queue pairs, we again got something really good performance-wise, right? You look at our graph, looks much nicer. All parallel lines. You look at the CDFs, the 3 lines are much more straighter. Remember, at 2 gigabits, there is still going to be some tail latencies. You're transferring larger and larger amounts of data, but it is now orders of magnitude better because we introduced more variability in the traffic. The network can load balance it much better than what you had earlier. Okay? And so that's our demos. This is how our customers use our tools. I showed you a live version with me driving it, but the same things can be done using automation. All the metrics can be pulled using APIs and incorporated into automated test cases. Everything that we show here, we've even embedded a Jupyter notebook in the application.
That's what I was wondering you're going to click on that.
There you go. And this is just a template that we provide, but you can pull more data using standard Python packages from your fabric and do more analysis right here if you wanted to. I'll just run what we have here, right? And you will see just very simple graphs that you wanted to, comparing the 2 trials that we just saw. Up to you as an end user, whatever code you want to do in Python, you can do right here.
The data that it's pulling from, what sort of database is it got?
We're just using pandas data frames right now.
That was like your second or third line in the...
Yeah.
Yeah. And I'm going to make sure I say this correctly. Your open traffic generators, is that part of any of these stories that you've told so far? Is it a...
No, that's a separate. That's a separate.
Okay, all right.
And with that, we come to our end of our presentation. Thank you very much. It was lovely presenting here on behalf of Alex and myself. And we look forward to seeing you at the OCP.